Hello, everyone. Welcome to the last GROOT talk of this summer. We'll be having Connor and Malin, who will tell us about Manifold Operads.
Thanks, Sarah. Okay, so I'd like to start with some motivation for the problem. So this is why I initially started thinking about this. It's a somewhat classical thing that's been on for a couple decades. So about 20 years ago, two people independently conjectured the following. So recall, En is the little dis operad, okay? And I, for now, will not define everything, just assuming that most people know what this is, and later on, I'll be a little more explicit with what everything is, okay? So En is the little dis operad, and people did some calculations, for example, like the homology of the little dis operad is equal to the Poisson operad, okay? And this is an operad because it's the homology of a topological operad. And it has a surprising property, which is that K of it, this is causal duality, this is defined to be equal to the bar construction. And then I take the dual. This is actually isomorphic to itself up to some shift. Okay, this is like a classical observation made that really made people interested in causal duality. Okay, some other examples of causal duality are well, if I take the causal dual of the Lie operad, this is equal to the commutative operad. And this explains, like for some part, this is like the rationale behind the fact that rationally spaces can be modeled as DG CAs or DG Lie algebras. I'll call that DGLA. Okay, and this is because causal duality essentially is telling you that algebras over the Lie operad are the same thing as algebras over the commutative operad because you have an equivalence like this. And so conjectured, so eventually at the same time, Ching and Salvatore in their PhD theses define bar constructions for topological operads / like spectral operads, and showed things like, well, this is let me not say that. And so then they conjectured that the same thing holds on the space level, okay? That the causal dual of En is up to a shift itself, okay? And right, the reason they conjectured this is because of the homology, because the homology is causal self-dual, okay? This turned out to be a very difficult problem. It's an easy thing to guess, but it's harder to actually prove. So recently, it became a theorem, again due to Ching and Salvatore, this time together, is that the En operad is causal self-dual. Okay, so again, I'll get into what K means. So let me highlight some things that are maybe not known. Okay, So K is this causal duality functor, which goes from operads to operads. This is in spectra. And this S negative N, this is a version of suspension for operads. So this is, again, operads and spectra to operads and spectra, okay? And so if you take anything away from my talk, the paper they write this in is very hard to read. Or maybe, let me say, instead of hard to read, it's very difficult. And there's a lot of kind of technical stuff in it, but one surprisingly technical aspect is that they explicitly construct up to, like, replacing by some equivalent objects, a duality pairing from the EN operad with the bar construction on it, which is a co-operad. I'll get into that as well. And this should take values in a sphere operad, okay? And so they construct this, and this is the difficult part. And somewhat easier is showing that the adjoint En to, well, this is now maps of spectra from B of En to Sn. This thing can be interpreted as a operad. This is an equivalence, okay? So that's like the argument in their paper, but it's done at a point set level with explicit formulae that are rather difficult, okay? And
what is Sn here?
So this is a sphere operad.
Okay.
I'll define that later. Yeah, okay. And so the difficulty lies in the formulas, in that, even though you have like an explicit formula, that doesn't make it easy to do things with it, okay? And so the motivation behind today's talk is to give a coordinate-free proof. Okay, so let me give you a caveat, which is that I cannot prove the full strength of their argument. Okay, so instead, let's give a weaker theorem, and that is that when I consider En, maybe let me put a box around this to denote that this is equal to an operad in the homotopy category of spectra. Okay, this is something that makes sense because the homotopy category of spectra has a smash product, and I can consider operads in it. So that's what the box is supposed to denote. We're going to have that En is equivalent to the causal dual of En shifted in the homotopy category, or as an operad in the homotopy category. So if there's a confusion in what I mean there, let me know now. This is a weaker result because this is not an equivalence of operads in spectra, but rather an equivalence of operads in the homotopy category of spectra. Okay, so that is what we're going to outline today. And so I probably said some stuff that may or may not be scary, like operad and causal duality, but the proof is very geometric, okay? And so the strategy of the proof is we're going to reduce the statement of causal duality to a version of a Tia duality, okay? And now it sounds like I just replaced Kazul by Atiyah, so probably it should just be it should be just as complicated. But actually, Atiyah duality is very simple. So let me briefly recall that. Okay. So the Atiyah duality is a theorem which I'll phrase as follows. Okay, so M is a manifold without boundary. Then we have the following. We have that M, if I take its suspension spectrum, is equivalent to if I take the 1-point compactification and dualize it, and then I should suspend by the dimension. So this should be like n-dimensional. Okay. So here, this is just something we understand. This is the suspension spectrum of space, and this is a suspension spectrum of a. Let me re-bracket this because it's a little confusing. Let me phrase this in a different way, which makes it more straightforward. So we know that there is a duality pairing between M plus and M plus, which takes values in the sphere. Okay. So this is a duality pairing. And a duality pairing means that if I look at the adjoint in spectra, so thank you so much. Yes, I said this. Yeah, thank you for pointing that out, Nikolai. That's a very important point. So let me I only need this for framed, so let me just assume that it's framed. Okay. So we have a duality pairing like this, which means that in spectra, the adjoint is an equivalence. So usually I'm going to write F to denote spectra. Okay. Sarah, people apparently can't talk.
That's odd. I have no idea why, but I'll look at the settings, I guess.
Okay. So this is saying that in spectra, when I take the dual, I get an equivalence. Okay. And then this dual right here is going to be the Spanier-Whitehead dual of M, and then it'll be shifted up n times. Okay. So this is like a Atiyah duality is like a space level version of Poincare duality. Okay. And now we're talking about like spectra and stuff, but this has an entirely geometric proof. So let me give you a proof of this. Okay. So first off, let me give you a definition. Okay. A loose framing of a manifold M is a section of this map. And this is evaluation at the origin. Okay. So in other words, if I have a picture of this, it means that if I take any point, in here, there's a corresponding copy of Rn embedded in it. Okay. And so I can do this. So I can make this choice globally. Okay. For example, any framed manifold, this means you're given a trivialization of the tangent bundle, any framed manifold is also loosely framed. Okay, and this follows from the exponential map. So you can pick a so you pick a Riemannian metric. This lets you talk about the exponential map, and then you can globally kind of pick a radius where the exponential map is injective, and this will induce a section of the framings of this map from the embeddings to M. Okay, so loose framings are not like an exotic thing. They're basically equivalent to trivializations of the tangent bundle. Okay, and so now we can just prove a Tia duality. Okay, so here's here's a construction, proof / construction of a Tia duality. Okay, let me denote. Okay, so let's call the loose framing F, and here's some notation. If we want to evaluate our loose framing at X, i.e. get an embedding from Rn to M, which sends the origin to X, we're going to denote this by Fx. So Fx is defined to be equal to F evaluated at X. Okay, so here's the construction, and again, let's write this. So this is going to be going from M smash with its 1-point compactification to Sn. Okay, and what we're going to do is we're going to take xy to the loose framing evaluated at X, and then I'm going to take the inverse image of Y. Okay, this is inside Rn. Okay, but then I can 1-point compactify Rn to get Sn. Okay, and so that makes sense if Y is in the image of f of x. So this is if Y is in the image of fx, and it's just going to go to infinity otherwise. So I can draw a little picture of what's going on here. Here's a manifold. Here's a point X. Here's a point Y. And then here's my loose framing evaluated at X. Okay, so f sub x. So what happens is that our loose framing will look at this square. It will set the blue point as the origin, and it will look at where the red point is. Okay, and then it will 1-point compactify this, and that gives us something in the sphere. Okay, so this map will be continuous. It will be well defined, and the claim is that the adjoint in spectra is an equivalence. Okay, and the proof of this is that it suffices to check it on homology. Okay, now here's a fun thing to like formally check. It's somewhat obvious in the case the homology classes are represented by submanifolds, but the general case is a little harder. So it suffices to check on homology, but if I take H star this pairing, this is Poincare duality pairing. which is so-called perfect pairing. And because you know, right, basically because homology interacts well with smash products, it turns them into tensor products. This will imply that the adjoint in spectra is a homology equivalence for all fields. Which is enough to know it's an actual homology equivalence. Are there any questions about that? Okay. Right, the point is a Tia duality is very simple. It's almost tautological. Cazul duality, on the other hand, is a somewhat complicated beast. Okay. So this is going to be about causal duality. Okay, so we're going to use a specific incarnation of operads. Okay, so I'll say recall, though I don't know how common a definition this is. If I and J are finite sets, and A is an element of I, the partial composition along A of I and J is defined to be equal to I, where I remove A and union it with J. So you think that you're replacing the element A by the set J. Okay, and so for us, our definition of operad. So an operad we'll use spaces or spectra will be an operad in spaces or spectra will be a sequence O. It'll be a choice OI for a finite set I, such that the symmetric group of I acts on this, along with these partial compositions. So I'll have OI smash OJ to OI union along A with J. Okay, and these should satisfy various associativity plus equivariance. Okay, similarly, we have cooperads. So we have a cooperad C. Well, it'll be CI with the symmetric group acting on it, and I will have maps going the other way. Okay, so these definitions.
Where's A in the above definition?
So A is an element of I.
Okay, so for every A.
Yeah. So this is for every choice of I, J, and A.
Okay.
Okay. And so this definition is well known to be equivalent to the normal definition of operads. So let me give an example. Okay. Okay. So En. This is the little dis operad. Let me draw some points in it. Okay. So this is an element of. Let me give some names to this. So I'll say A, B, C. So this is an element of En of ABC. And I can give another element. say D, E, and I can form their partial composite along ABC union along A with DE. And the composite here is I just insert the right factor into the left factor. So the output will be this. And I'll have two smaller cubes inside here. Not to scale. Anyways, so the partial composite here is just inserting one cube into another cube. So the little dis operad is one of the most famous operads. There's another operad which is called the Fulton-McPherson operad. So the operad Fn of I is defined to be equal to it's a certain compactification of the following. It's probably easiest for me to just draw you a specific point. Okay, so inside Fni is going to be diagrams like the following. I will have configurations, and these would be possibly infinitesimal, meaning that I can blow them up and I can find other configurations inside here. And I could do that in multiple places, as illustrated here, or I could do it at multiple layers. There are certain conditions that these must satisfy, but the important thing to get is that this Fni, it's a manifold with boundary. Yeah, it's a manifold with boundary, and then hopefully the composites should be somewhat obvious. But the idea is, if I have a configuration, here's a configuration of points, here's another configuration of points, and then if I pick a specific point here to do my partial composite, this will get sent to this. Okay, and so this is kind of like a tautological almost, I just put the pictures together. And so what we can take away is that Fn I smash Fn J to Fn I union along A with J. This is actually, so sometimes these things don't have a natural base point. So I'm going to add a base point to each of them. And if I forget, you should just imagine that there's a base point that's added disjointly.
So these are actual topological spaces?
Yeah, these are topological spaces.
Okay.
So yeah. So the interior of them is a type of configuration space. And then there are boundary points, which are these infinitesimal configurations. Thanks for the question. So this modulo this extra base points, this is actually an embedding. It's a boundary inclusion. It's an inclusion of part of the boundary. And that's what makes this this model, or that's what makes this operad so well behaved, like kind of homotopy theoretically, is that the operad composition maps actually end up being inclusions of the boundary. And so, right, so what's the important fact about this? Okay, so it turns out, and this is proved by Salvatore, it turns out that the operad Fn is equivalent to the little dis operad. And this is like morally true because both of these things are equivalent to configuration space. Both of these things are equivalent to configuration space, but the difficulty in like operad theory is actually constructing maps that respect the operad structure. So it turns out that you need to introduce a new operad, W of En, which is like kind of a cofibrant replacement, and you have a little triangle like this, and that's what gives the equivalence. Anyways, okay, so I should tell you what causal duality is. Okay, so here's a definition. Okay, so if O is an operad, this should be in like spaces, but it makes sense in spectra. Then we have the following. Okay, I can define B 101 is equal to the spaces of trees. So this is going to be a collection of weighted trees. So let me write the definition, then I'll draw you a picture. So this is weighted trees with labels in O, such that if any edge is infinity, we identify with the base point. Or if the root is 0, the root length is 0, we identify with a base point. Okay, and then finally, if a different edge length is 0, we collapse and apply the operad composition. Okay, so that was a mouthful. The point of the definition is that it allows us to consider spaces of trees. Okay, so here's an example. I would draw a tree like this. Okay, and I should have labels at these vertices. So maybe I'll have E1 here, E2, E3, and then I should additionally have weights for these for some of the edges. So there'll be a weight here, there'll be a weight here, and then let me say that this one's 0. Okay, and then this would be identified with the following tree. Where I've collapsed the edge, and so now this will be like E2 composited with E3 along along the left leg. Okay, so the reason we're allowed to define this is because operads are associative. Yeah, they're associative, and they have the correct like equivariance properties. And so, I mean, what's the importance of the bar construction? Well, one thing, one fact about the bar construction is that it models the derived indecomposables. Up to a suspension. So this is going to be the indecomposables of O. And so, you know, it like taking indecomposables, and it turns out is like a super important, you know, fact of life in algebra topology. And so like, you know, that we have a geometric model of the indecomposables is pretty nice. But there's a more important property, which it turns out that this this bar construction is actually a co-operad. Okay, so the bar construction is a co-operad in the following way. Okay, so let's see if I can select this. All right, congratulations to me. So this is a co-operad. So let's try to split. Well, you know, it's hard to do this stuff without giving like names to everything. So this will degraft. If I pick like an edge, so I'll just like kind of slice here. If I degraft, this will give me trees like follows. Okay, and I can keep the edges the same. T1, okay, well, this one's like 0, and then this one is going to be T2. Okay, so this is a specific example of a decomposition where I'm splitting along the red line. So then if the degrafting doesn't make sense, so you could imagine that it's asking you to split kind of in a way that the tree doesn't allow. So if degrafting is not possible, we send it to the base point. And so it's not wholly obvious like that this stuff is actually like continuous. And this is part of the reason why we have to take so much quotients in the definition of the operad. You know, Ching and Salvatore independently prove this gives a co-operad structure on the bar construction. And this is like the start of, this is basically the genesis of Cazul duality for operads in spaces and spectra. Well, more so in spectra. It turns out Cazul duality isn't super well behaved in top. It is in spectra. So let me define Cazul duality. Okay, so if O is an operad in spectra, then we define K of O to be equal to the bar construction of O. That's a co-operad, and if I dualize it, it becomes an operad. Okay, and so to recall what we kind of want to prove, we want to prove that the Cazul dual of En after I suspend is equivalent to En. Okay, and we want to take this in the category of operads in the homotopy category. Okay, so I promised you a discussion of manifold operads, and that's going to be the major driver in this proof. Okay, so I'm going to be a little loose with talking about operads in spectra versus operads in the homotopy category, just for the sake of time. Okay, so let's define what a manifold operad is. Okay, so a manifold operad is an operad O in spaces. This is actually without a base point. So I should be taking products. A manifold operad is an operad O in spaces such that for all finite sets I, OI is a manifold without boundary, and the partial composites are codimension 0 embeddings. Okay, so there's two conditions. Everything's a manifold, everything's an embedding. Okay, so here's some examples. If well, this is like kind of the driving example, or it's one of the driving examples. There's a operad structure you can put on the Euclidean on Euclidean spaces. So this is called the Euclidean operad. It's defined to be I take k copies of Rn, and then I mod out by translation. So I mod out by shifting everything in the same direction. Okay, and so then I can make this an operad.
Are these RNs like planes inside some bigger R something?
Sorry?
Are these RNs planes in some other R something?
I don't really understand the question. I mean, I guess no.
What does it mean to mod out by translation?
Yeah, so it's like, so if I had like one, if I was just giving you some numbers, 1.5 to this is going to be equal to it's going to be equal to like 2.53.
Oh, okay.
Okay. Yeah, thanks for the question. So it's just by adding a constant like vector to everything. Okay, and so these are operads in the following way. If I have like a tuple of points here, and I'm trying to insert here, and I want to insert another tuple of points. Okay, what I do is I basically look at the let me make this a little more complicated. So what I have to do
is this like Rn to the K modulo like a copy of Rn?
Yes.
Okay.
Yes. Sorry, I'm making sure. Yeah, it should just be a single copy of R. Sorry, I there's like some yeah. It's not a single copy of R. It's a single copy of R to the N.
Yeah. Cool.
Okay. Okay. So if I want to insert, if I want to do like a composition here, what I have to do is I have to calculate what you might call the corner of this tuple. So I just look at all of the coordinate wise like kind of minimums, and I'm finding like basically the corner of the tuple, and I take that corner and I'm going to translate it to the circled dot. So this will go to it'll look like this. Okay, so I translate this whole picture into the red dot, and then I erase the dot. Okay, it turns out that these structure maps give homeomorphisms, and so this will be an example of a manifold operad. Okay, and so earlier it was asked about what the sphere operad should be. So one thing we can do is that there's a more general construction, which is if I have a manifold operad, or moreover, if I have an operad where the compositions are open embeddings, we can consider a co-operad O plus, which is defined to be equal to, I take the ith space and I take its 1-point compactification. Okay, so this is a co-operad. Okay, so this is because this functor plus well, it's actually is contravariant with respect to open embeddings. Yeah, so this is like a classic thing, like, you know, in kind of homotopy theory, when you're doing these Pontryagin and Thom constructions and the like, when I take a 1-point compactification, it'll turn stuff around if that stuff is open embeddings. And so in the case of Rn, this operad we just constructed, Rn plus, this we're going to define to be the sphere co-operad, but this is actually this thing right here is both a co-operad and an operad. And that's because the structure maps are homeomorphisms, because the composites are homeomorphisms. So normally I would get a co-operad, but if the composites are all homeomorphisms, it'll also be an operad. So the sphere operad is just the 1-point compactification of the Euclidean operad. Okay, so let's get to the meat of things. So the first thing, and I'll go really fast here. So there's a notion. So there's a notion of a framed manifold operad, and this is designed to make designed to make the following true. Okay, so if O is a framed manifold operad, we're going to have an equivalence. O is equivalent to O plus dual. Okay, this equivalence. So this is an equivalence of operads, and it is the exact same. The exact same as the Tia duality I showed you earlier. We'll have some type of loose framing for our operads, and we'll give a tautological pairing as before. And so this is really the easiest part of the proof. Thank you again, Nikolai. Right, this will have a shift of Sn. So I'm going to take the sphere. So I called this Sn, the sphere operad, and I'm going to smash that with O plus dual. Okay, this is because, like, you construct a pairing which takes values in Sn, and so that will account for the shift of n. So thank you for that, Nikolai. And again, when I take duals like this, implicitly what's happening is that I'm taking sigma plus infinity. Thank you so much. N is equal to the dimension of the second space of the operad. The first space of the operad will be like just like a point. Okay, yeah, thank you so much. Okay, so we're gonna have a shift like this, and this is an easy theorem. And like, so here, see, I'll tell you where the trick comes into play. So the trick is actually getting a manifold operad which is related to the bar construction. And so what we're going to do is give the following definition. Okay, so if O is an operad, define W W0 infinity of O. This is going to be equal to, it's going to be equal to weighted trees as before, except we're not going to, so it's going to be modulo the same relations. Except for the root length 0 condition and the length infinity condition. So we will never, like, there can be length infinity edges anywhere, and the root edge can be anything, and we don't identify it with a point. Okay, and so now this thing, this is an operad. It's an operad as follows. If I have a tree like this, and I have another tree like this, I can graph them together. I can graph them together to get a tree like this. Okay, and I'm going to graft, you know, yeah, it's really grafting, and you just like preserve the same edge lengths. So none of the root edges, so these ones I marked as like purple. These guys don't have weights attached. And so when I graft, I'm going to be giving the weight of the root edge. Sorry that I'm going a little fast here. And the point of this observation, so it is to have the following, the bar construction on O. This is isomorphic to the 1-point compactification of this W construction on O. Okay, and so here's like the first interaction between kind of our causal duality and the T duality is that it can be computed as a 1-point compactification. So B is a 1-point compactification. Okay, and so here's the nail in the coffin. It's this really cute result of Salvatore. Okay, this is by Salvatore. He actually shows that for Fn is isomorphic as an operad actually to WFN. Okay, now that's a super weird result, let me tell you that. But anyways, it's true, and in particular, so particularly WFN is a manifold, which is not obvious at all. And this operad I just defined, W0 infinity Fn, this is, yeah, so oh, did I, no, so sorry, you know, I'm like rushing a little bit. So there's a notion of a W construction, so this is called the W construction. That's like a cofibrant replacement for operads, and so that's like something where it's like what I just told you, but you don't have a root edge length. And the W sub 0 infinity is when I include a root edge length. so it's like a really small like difference. But the effect is that W zero infinity gives me an operad where all the compositions are open embedding. So I can take the plus, I can take the 1-point compactification of it. Yeah. So in particular, like I have to basically thicken it up to make it a manifold operad, because otherwise it won't be codimension zero embeddings. So WFN is a manifold, and W zero infinity FN, when I thicken it up, is a manifold operad. So I should have a space here. Okay, so this is a manifold operad. Okay, and so it will turn out, so kind of theorem, this thing is a manifold operad, and it's framed kind of up to some homotopy issues. So this is like basically framed up to homotopy, whatever that should mean. And so we will apply a Tia duality to it. So a Tia duality up to homotopy means that I basically have the statement of a Tia duality, but with brackets around it. So I'll have W zero infinity Fn is equivalent to, and I will get the shift right here. This will be equivalent to a shift of the 1-point compactification of it dualized. Okay, but as we just mentioned, the 1-point compactification of that is the bar construction. And so this is the result I claim to have at the beginning. And so, yeah, thank you guys for listening. Thanks for all the questions. Yeah.
Let's all take a moment to thank Connor.
Thank you.
Are there any questions? And sorry, Nikolai, about the speaking thing. I wasn't able to figure out what was going on with that.
At a certain point at the beginning, you 1-point compactify a manifold.
Yeah.
That does not play well with the smooth structure, which you need, right?
So are you asking if there's like issues when I 1-point compactify, or do you have a specific?
I'm asking if I mean, you start with a smooth manifold, then you go somewhere else because you're 1-point compactifying, and then somewhere there.
Yeah, so there's no, like, in general, like, yes, the 1-point compactification of a manifold will not be another manifold. And this is not really an issue. It's like the point isn't to say that like a manifold is dual to another manifold, because like in this case it's not. It's dual to its 1-point compactification. There does exist like settings where like you have like singular manifolds, and like 1-point compactification now actually like sends you, like, it kind of is an endo functor when it like originally like isn't on manifolds, but that's not an issue. I mean, basically the only time I use the fact that it's a manifold is to have the loose framing, and the loose framing is like defined on the left factor of the pairing. You don't need it for the right factor. So even though there might not be a Euclidean neighborhood around infinity, I don't use it because I don't have that kind of problem point in the left factor where I actually am using my loose framing.
Okay, perfect. Thank you.
Any other questions for Connor?
I got a bunch, but maybe it's better we talk after. He's,
Yeah, sure.
Yeah.
Um,
Uh,
yeah,
Well,
yeah.
shall we perhaps thank Connor again then?